Organic molecules get classified into a wide range of different families known as homologous series. And this video introduces you to a range of these homologous series: the alkanes, the cycloalkanes, the alkenes, the arenes, the alcohols and the ethers. And by the end of this video you ought to know the characteristic features of those homologous series, and if shown the structure of a molecule, you ought to be able to identify which of those homologous series it belongs to. So let's start by making clear exactly what we mean by the term homologous series. A homologous series is a family of organic molecules which share common characteristic structural features and are different only really in the number of carbon atoms in the molecule. So for instance, here is one homologous series. You can see they all just consist of carbons single bonded to other carbons and to hydrogens, and they vary by the number of carbons in the chain. Getting a little bit more advanced, this is another homologous series, the alcohols in this case, and you can see that each molecule here has this COH group in it, and then there's variations on that simply in terms of the number of carbon atoms. So let's look at some of these homologous series, and we'll start with the simplest one, which is known as the alkanes. A typical example of the alkanes homologous series is shown here, and from it we can see some of the key features of alkanes. One is that they only contain carbon and hydrogen atoms, and there's a technical term you need to know for that, which is that they are hydrocarbons. So hydrocarbons are any molecules that contain only carbon and hydrogen atoms, no other elements present. Another feature of the alkanes is that they only have single bonds in the molecule. Carbon-hydrogen bonds can only be single, so really the bonds we're looking here at the ones between the carbons. All the CC bonds are single. And again, there is a technical term for this, which is that the molecules are saturated. So if you've only got single bonds between the carbons in a molecule, it's a saturated molecule. If you have any bonds between carbons that aren't single, then we would call it unsaturated. We can also describe alkanes in terms of their general formula, and this fits the pattern CnH2n plus 2. The n here is simply the number of carbons, so however many carbons there are, n, there'll be twice that plus 2 hydrogens. Let's look at an example of that. So if we take an 8-carbon alkane, its formula will be C8, and so the number of hydrogens is calculated as twice 8 plus 2, so 16 plus 2, and that is 18. So C8H18. The previous slide showed a very simple alkane, and we need to recognise that the family, the homologous series of the alkanes, contains rather more complicated looking molecules. Complicated largely because they can be branched in structure. What do we mean by that? Well, 3 examples here. So rather than just a continuous chain of carbons, you can have side shoots coming off, so to speak. These are full structural formulae. You might want to pause the video at this point and just think about how you would draw those as skeletal formulae. And they'll look like this. So the first one, something like this, you might have drawn it the other way up, and the second one like this, and the third one, well, there's an interesting thing of attaching the two one carbon branches sticking off to the same carbon, and that tends to be drawn like that. Alkanes are supposed to fit the general formula CnH2n plus 2. So do branched alkanes still fit this? Well, they have to be alkanes, and if you count up in each case, yes, they do. The next homologous series we'll look at is the cycloalkanes, and these are very similar to the alkanes. There's a clue in the name to the difference, and that is that they are cycles. They're ring structures. Instead of a chain of carbons, they're joined round to make a ring. This is the full structural formula of a 5-carbon cycloalkane. If we did that as a skeletal formula, rather attractively, it's just a regular pentagon. So how can we describe cycloalkanes? Well, like the alkanes, they are hydrocarbons, and also like the alkanes, they are saturated. So remember, a hydrocarbon because they contain only carbon and hydrogen atoms, saturated because the bonds between the carbons are single bonds. And the general formula in this case, well, we've lost the extra carbon, the extra hydrogen that was attached to each end of the chain. So that +2 bit of the general formula goes, and cycloalkanes are just CnH2n. What's shown here is a very simple cycloalkane. You can have other groups, chains of carbons or other atoms sticking off the ring, and you can still call it a cycloalkane. Next up in our tour of homologous series is the alkenes. A very small difference in the spelling between alkenes and alkanes, and you need to make sure when you talk about these homologous series that you write very clearly so that it's obvious which one you're talking about. What is it that makes an alkene an alkene? Well, they have, somewhere in the structure, a double bond between two carbons, at least once. So what's shown here is the simplest possible alkene. You can't have a one-carbon alkene, and so this is the simplest one. Some other members of the homologous series are shown below. And you can see from the bottom one that you can have more than one double bond between carbons. So alkenes, compared to alkanes, very similar again, but somewhere in the structure, at least once, there'll be a carbon-to-carbon double bond. It's important that you specify it's a carbon-carbon double bond, not just saying a double bond, because you can get double bonds between carbon and oxygen and other elements, and that does not make it an alkene. How do we describe these using some of our vocabulary again? Well, are they hydrocarbons? Yes, only carbon and hydrogen atoms. Are they saturated? No. We've got this double bond present between carbons, and so we'll describe alkenes as unsaturated. So that's a key difference between alkenes and alkanes. Alkanes are saturated molecules, alkenes are unsaturated. We've talked about general formula before. The general formula of the alkenes can vary somewhat depending on how many double bonds, carbon-carbon double bonds, are present. If there's just one carbon-carbon double bond, the general formula will fit the pattern CnH2n, twice as many hydrogens as the number of carbons. But if you've got a molecule with more than one carbon-carbon double bond, then actually the number of hydrogens keeps decreasing. Another homologous series that you need to know about is the arenes, and there's really only one main example of the arenes that you'll meet, and that is benzene, which is drawn as a hexagon with a circle in the middle. That's obviously a skeletal formula, but that's all you ever draw for benzene. You don't draw a full structural formula for it. The hexagon is obviously a 6-carbon ring. The circle in the middle, well, you'll learn more about that later in the course. But it shows the presence of 6 extra bonding electrons, which are delocalized around the carbon ring. So the bonding is kind of a cross between single bonds and double bonds. You've got the normal single bonds and then these delocalized extra electrons. Don't worry too much about that now. That'll be explored more during the course. So benzene is the simplest arene that you need to know about. And you'll find it present in more complicated molecules. So the kind of things shown here. So we'd still consider these to be arenes because of the presence of the benzene ring in the molecule. Describing arenes again using some of our vocabulary, they are unsaturated because the carbon-carbon bonding is not just single bonds. The hydrocarbon idea, well, if you've just got benzene on its own, that's carbon and hydrogen atoms. The formula of benzene is C6H6. There's just one hydrogen attached to each carbon in the ring. Anytime you join something else onto the benzene ring, one of those hydrogens is lost. And it's got a new word for us, and that is aromatic. Anything with a benzene ring in it, so anything with an arene present in the structure, is called aromatic. With everything else being called aliphatic, spelt as shown there. So if there's a benzene ring in the structure, you can say it's an aromatic molecule. If there isn't a benzene ring in the structure, then you'll describe it as an aliphatic structure. Well, we'll move on to another homologous series now and finally meet one that doesn't just have carbon and hydrogen in its structure, the alcohols. and they all have the characteristic feature of having one or more of the hydrogen atoms along the chain replaced by an OH group, so bringing an oxygen atom in. A typical alcohol is the one shown there. That's ethanol. That's actually the alcohol that you get from fermenting sugars. And you can see how one of the hydrogens, the one that would be at the left-hand end of the carbon chain, has been replaced with this OH group. There's plenty of others in the homologous series. Skeletal structure there showing that you can have more than one OH in the molecule. In terms of the vocabulary now, this is clearly not a hydrocarbon. So alcohols are never hydrocarbons because they've got oxygen present as well as carbon and hydrogen. And in fact they get referred to, along with other things with oxygen in the structure, as oxygenates, and are useful in fuels for that reason, more oxygen to support combustion. In terms of some of the other vocabulary, well, you can describe an alcohol as saturated if there isn't a carbon-carbon double bond or a benzene ring somewhere else in the structure of the molecule. And you could also describe an alcohol as aliphatic, again, if there isn't then a benzene ring somewhere else in the structure of the molecule. Having introduced the alcohols, we'll just look quickly at another homologous series which is very similar to the alcohols, and that's the phenols. If you look at the example here, it's got the OH group like an alcohol. The key thing here is that the OH is directly bonded to a benzene ring, and when that occurs, actually that is not an alcohol. Its chemical properties are very different to what you'd expect from alcohols, and so you cannot describe this as an alcohol. It has its own name. It belongs to the phenol homologous series, and actually this molecule itself is called phenol. So you mustn't call that an alcohol. It's the kind of exception in a way. It can have other attachments, so here you see phenol with other things, the bromine and the carbon side chain attached. And just going sort of in the other direction, sometimes you can think something is phenol when it isn't. It's actually an alcohol. So this final molecule drawn isn't phenol. That you would call an alcohol. And if you look carefully, you can see that although there's a benzene ring and an OH group, the OH is not directly bonded to the benzene ring. It's bonded to another carbon, which is then bonded to the benzene ring. So for phenol, you have to have the OH directly attached to the benzene ring. So we've reached our final homologous series for this video, and that is the ethers. A typical ether is shown there, and the key feature of an ether is this COC group. So a carbon bonded to an oxygen, which is then bonded to another carbon. Note the difference between that and an alcohol. Alcohols have a carbon bonded to an oxygen, but then the oxygen is bonded to a hydrogen. So in a way, if you want to think about it this way, ethers have an oxygen as part of the chain, in amongst the carbons, whereas alcohols have the oxygen sticking off the chain as part of an OH group. If we're going to draw that skeletally then, we actually have to include the O of the ether in the zigzag of the chain. So we just put it where normally a point of the zigzag would be, and that shows that instead of a carbon at that point, there's an oxygen. Using some of our technical vocabulary, is an ether a hydrocarbon? Hopefully you're saying no, it's obviously not. It's got an oxygen in it, and instead we can refer to it again as an oxygenate, like an alcohol. Is it saturated? Well, yes, as long as there isn't a double bond, a carbon-carbon double bond, or a benzene ring somewhere else in the structure of the molecule. And is it aliphatic? Again, yes, in and of itself, as long as there isn't a benzene ring attached somewhere else along the structure. So far we've been talking about homologous series and which homologous series a molecule belongs to. You can also be asked to talk about the functional group in a molecule, and so we'll just take a moment to see what that means. A functional group is the region in a molecule that's responsible for its chemical properties, so the group of atoms that takes part in the characteristic reactions of that kind of molecule. And actually the language we use here is mostly identical to what we've been using for the homologous series. So let's look at some examples. The structural feature and then the name of the functional group that represents. So if you've got a carbon-carbon double bond in a molecule, that's known as an alkene functional group. So the same name that you give to the homologous series the molecule belongs to. If you've got a benzene ring in a molecule, that's called an arene or a benzene functional group. If you've got this OH group attached to a carbon, it's called an alcohol, or we've got this new word, hydroxyl. So you'd say the molecule belongs to the alcohol homologous series, but you can refer to that particular group as either an alcohol functional group or a hydroxyl functional group in the molecule. If you've got the COC, that's the ether, the same name as the homologous series the molecule belongs to. And if you've got an OH directly attached to a benzene ring, again, that's a phenol functional group, the same name as the homologous series the molecule belongs to. Here's an opportunity now to see how well these ideas have sunk in. You're going to see a series of molecular structures, and in each case these are the same questions. Which homologous series does the molecule belong to? Is it a saturated molecule or an unsaturated molecule? Is it a hydrocarbon, and is it an aromatic or an aliphatic molecule? So pause the video now and answer the questions for this molecule. So hopefully you spotted that it's an alkene with the carbon-carbon double bond. Notice how I've written the E nice and big in the middle of alkene. It's worth doing that when you're answering exam questions, just so it's obvious you're not writing alkane. Saturated or unsaturated? Well, it's unsaturated with the carbon-carbon double bond. It is a hydrocarbon. It's only got carbon and hydrogen atoms. Obviously the hydrogens aren't shown because we've done it in the skeletal format, and it's an aliphatic molecule because there is not a benzene ring present. So here's the next one in the full structural format this time. Pause the video and answer the questions. So hopefully you spotted this time it's an ether with the oxygen between the two carbons in the chain there, so not an alcohol. It's a saturated molecule, no carbon-carbon double bond. It is not a hydrocarbon, it's actually an oxygenate in fuel terms, and it's an aliphatic molecule because there's no benzene ring present. Another one, again, pause the video, answer the questions. And you should have spotted that this is a combination of a cycloalkane with an alcohol group attached. Easily confused with phenol, where the OH is attached to the benzene ring, and although this is a 6-carbon ring, it's not benzene because it does not have that circle drawn in the middle to represent the 6 delocalized electrons. So this is just a cycloalkane, single bonds between the carbons, and then there's the OH bonded onto that. It's saturated, no carbon-carbon double bonds. It is not a hydrocarbon, it's an oxygenate with the oxygen present in the molecule, and it's aliphatic because there's no benzene ring present. Last chance to practice then. Again, pause the video and answer the questions. So hopefully you spotted this belongs to the arene homologous series, or you could say benzene. It's got the benzene ring there, the hexagon with the circle in it. It's got a carbon chain attached on the side as well. That doesn't really change anything. With the benzene ring present, it's unsaturated. The bonds between carbons are not just single bonds. It is a hydrocarbon. There isn't any other elements apart from carbon and hydrogen present. Obviously, again, we can't see the hydrogen because it's been drawn in the skeletal view where you leave the hydrogens out. And this time it's aromatic because there is a benzene ring present in the structure.